So welcome back again to the class on timing analysis, static timing analysis. So in the last lecture we have seen that what are the basic definition, why we will go for static timing analysis instead of dynamic timing analysis, and what is the usefulness of doing this timing analysis, and then some of the basic terminology which are associated with timing calculation, then like false path, multi-cycle path, then setup time, hold time, all these things. Then again we will see some other timing definition too, like one of them is like clock latency. We have said this clock latency in design compiler. So what is clock latency? Clock latency means the delay between the clock source and the clock pin. That means from the clock pin is external to the chip. So from the clock pin to the the clock source, what is that means time it is taking, so that is known as clock latency. So this is called as source latency of the clock. Normally it specifies the skew between the clock generation point and the clock pin. So then rise time and fall time. What is rise time and what is fall time? Setup time and hold time we have seen. What is rise and what is falls? So fall. Then it is rise time is defined as the time it takes for a waveform to rise from 10% to 90% of its steady state value. That means, as we know that change from 0 to 1 or 1 to 0, that is not abrupt. Okay. So that means in ideal case what we see that 0 to 1 the transition is like very much linear, but it does not happen like a straight line. So it takes some time to reach from 0 to 1. Okay. So that's why this rise time is the time which is taking for the signal going up from 0 to 1, from 10% to 90% to the steady state value, and the fall time is that means the time which has been taken for a waveform to rise from 90% to 10% of its steady state value. Okay. So that means 10% to 90% is the rise time, and 90% to the 10% is the fall time. So that means whenever that is the signal is coming 1 to 0. So then clock to Q delay. What is clock to Q delay? In a resistors or in a D flip flop, from the clock pin there is a clock source to the resistors and there is a output which is Q. So that clock to Q delay is the delay from rising edge of clock to when Q becomes available. So it depends on the input clock transition as well as the output load capacitance. That means from applied the clock is available, so whenever the positive edge or negative edge, the edge of the clock occurs, so after how much time or how much delay the output is basically available from that particular resistor, so that is known as clock to Q delay. Then clock skew. What is clock skew? It is defined as the time difference between the clock path reference and the data path reference. The clock path reference is the delay from the main clock to the clock pin, and the data path reference is the delay from the main clock to the data pin of the same block. That means from the clock pin, the clock is basically connected to each of the registers or each of the elements, sequential elements, right. So there must be the delay, it will be the difference of this delay, where this clock path reference is the delay between the main clock pin, that means from main clock to the clock pin, that means clock source to the clock pin, and the data path reference is the delay between the main clock to the data pin which is connected to the clock. Okay. So that's why that means there will be a delay between this whatever clock is at the source, whatever clock pulse is arriving, and in the data pin what the clock is arriving, so there will be a skew. So then what is metastability? Metastability is a condition which has been caused when the logic level of the signal is in an intermediate state. That means what I said that during the setup time and hold time violation, so when the clock edge occurs, so in between this setup time and hold time, if the data changes its value, that means if the data is not stable, so at that time the corresponding sequential element, it cannot recognize the data properly. So it is, that means at that time the data, that means or the output from the register, that becomes in a ambiguous state. So that state has been known as the metastable state. So then critical path. So what is critical path? The clock speed is normally determined by the slowest path in the design. So this is often called as critical path. Critical path you may that means define in other terms, that means the path which is taking maximum time for applying the input to the getting the output. So that is the maximum path it is traversing in the corresponding chip. So that is known as critical path. Then what is clock jitter? Clock jitter is the variation in clock edge timing between clock cycles. So it is usually caused by noise. That means it may happen that okay, the clock pulses are not, that means whenever the clock source is coming to the pin, so at that time it may happen that each of the clock pulse that is not same. So there is a little bit difference between each of the clock pulse which is coming in a row. So that difference is basically known as this clock jitter. So and then setup time and hold time, we have already seen the definition of it. Then interconnect delay. What is interconnect delay? This is the delay which has been caused by the wires or the nets. Interconnect introduce three types of parasitic effects: capacitive, resistives and inductives, all of which influence the signal integrity and degrade the performance of the circuit. So that means whenever we are connecting from one block or one cell to the another block, so it has to connect through the wire or it has to connect through the net. So each of the net introduce the capacitive value, the resistance value as well as the inductive value. So for that, if the net length is, and depending on the length, this basically increases. So whenever this net as these nets are introducing these three that means things, these three parasitic effects, so these three things degrades the performance because this affects the signal integrity of the corresponding design chip. So that's why this interconnect delay is also one important factor in timing analysis. Then negative setup time. In certain case, due to the excessive delay, like it can be caused by a lot of inverters in the clock path. As we said in the hold time violation, how we can remove the hold time violation? We can do, or we can put some extra buffer on that particular clock path source or on that particular clock path. So if we heavily loaded on that, that means if we put too much of buffers on the clock path, so at that time what will happen? Excessive delay will occur at the clock source or the clock path. So at that time the clock signal actually arrives later than the data signal. The actual clock edge, you want your data to latch arrives later than the data signal. So this is called as negative setup time. That means though whenever we are fixing the hold time violation, so at that time we must be very much careful so that this negative setup time that doesn't occur. So then negative hold time, it basically allows the data that was supposed to change in the next cycle change before the present clock edge. Then negative delay, it is defined as the time taken by the 50% of the crossing to 50% of the output crossing to the 50% of the input crossing. Then transition time, again all are basically related to clock only. It is the time taken for the signal to go from one logic level to the another logic level. Then delay time, what is delay time? It is defined as the time taken by the 50% of input crossing to the 50% of the output crossing. Then insertion delay, what is insertion delay? Delay from clock source to the sequential pin. So these are the basic timing actually definition or the basic terminology which are associated in timing calculation. Suppose you take one example. This one is one example. Suppose two flip-flops are there, in between of them there is one combinational circuit, right? So now if you see that the change in the signal data caused by the clock transition at flip-flop 1 and this flip-flop 2 before the following clock edge arrives at flip-flop 2, so that the logically processed data can be reliably latched into flip-flop 2. So, that means how this whenever we are putting this 2 flip-flop here, just a second. So, this is one flip-flop and this is another flip-flop, right. In between of them there is this combinational logic. So, whenever this clock edge has been, this is also connected with this is also connected with that means the another resistors. So, and you see the output of this that passes through this combinational logic and then it is the input to this. So, this kind of circuit may give you that violation. So, why violation? Because if the delay for this combinational logic is that means very much heavy. So, at that time this clock period, this on that particular clock edge, the data here that may change, or the if the corresponding output from this logic, the data changes very abruptly. So, at that time you can get the corresponding, that means effect here at flip-flop 2. So, what are the effects and how it occurs? If you see the waveform, so at that time we will see. Okay, so this is, let us consider this is the clock edge, this is the clock source, right, which is connected to flip-flop 1 and flip-flop 2. So, this is then this is the flip-flop 1 D, that means this is the D input which is coming from the external signal to the flip-flop 1. Okay. Then what will be the output from this flip-flop 1? What will be that flip-flop 1? Q. So, you see this one is the D, this one is the D input, okay, to flip-flop 1, and what is the Q? So, here Q is the, Q will occur where? Q will occur only at this clock edge. Whenever we are getting the fast positive edge of the clock, then at that time it will check whether what is the values of the data. So, here the values of the data is 1. So, that means after some time, so that means what is the value of hold? So, after some time this value, this flip-flop Q will be gone to the 1 state, okay, right. Then again another clock edge occurs here. So, at that time what is the value of, that means data here? 0. So, again after some time the data will be come to 0. So, that means for Q output, now this is the output. Now, this Q has been passed through a combinational circuit. So, that means the delay for this combinational circuit is, okay, not from this one, actually from this particular point to this particular point, this is the combinational delay. Because of this combinational circuit, I am getting the delay in this Q. Now, this is the input to the flip-flop 2, right. So, flip-flop 2 at this edge, at this particular edge, now this is the input to the second flip-flop. So, here as it is that means the value is stable here, and as this is 1, so after some time it will be gone to 1. So, this is flip-flop to Q. So, now you see the terminology which are we have already said that, okay, what is this, that means setup time and hold time and all those things. So, whenever we have applied at the very fast, that means this is the fast clock edge, when the input data has been captured or input data has entered into the corresponding circuit, that means into the fast flip-flop element. So, that is why this is known as the launch edge. Okay. So, then this one, the second clock, that basically that data has been processed by the flip-flop 1 and it has been processed through a combinational circuit, and after that it is the input which is going available to the second input. So, at this particular edge This is known as capture edge, where this data which has been already input to the flip flop 1, that has been captured in this particular edge. So that is why this is known as the capture edge. So you see the data basically launched at this particular by flip flop 1 at this event, and this is the data capture event at flip flop 2. Okay. So while launch, that means as it is passing the data to the second flip flop. So that is why it is launching the data. Now that data has been again captured by the second flip flop. So here you see this is the actual arrival time of the data. That means input data has been passed through this, then combinational circuit, then combinational circuit. So this is the actual arrival time of the data, but the required time is this one, because this is the setup time. Here this clock edge occurs. Okay. So this is as this one, this is the setup time. So before that, here I need, before this the data should be stable, but the data is stable much before than that. So this part is basically known as the slack. That means it is the difference between the required time minus the actual arrival time. So if the actual arrival time is more than that, that means the required time, at that time you will not capture the data, because if the delay is more, so at that time what will happen? This will, if this comes under after this, so at that time this one cannot be captured by this second clock edge. So at that time you will get the slack as negative, so which is not at all tolerable in the chip design. So at that time again what you have to do, you have to increase the clock period, or again you have to optimize the combinational circuit so that this delay or the data must be stable before its required time. Okay. So here actually this is the one example has been taken to show you, okay, that this one actually how we calculate the delay, how we set the corresponding clock period, and what is the values of setup time, what is the rise time, what is fall time, how they are affecting in the timing information. Okay. So then again you see another example. So here you see that, okay, the clock A and clock B, they are connected with the same clock, but clock A and clock B is different. Why? Because in between this there are 3 inverters are placed, or 3, sorry, not inverters, 3 buffers has been placed. But in this case, in this path, only one NAND gate is there. So this corresponding path delay for this Q to D, that is much more shorter than the corresponding delay of this 3 inverter. So at that time what will happen? At that time what will happen? So if I, that means waveform wise if I calculate, so at that time what will happen? This is the launch edge. So after some time, okay, so this is the that means this is the clock B, as the inverters has been placed in between, sorry, buffers has been placed in between. So flip flop 1, this is the input data, the same data. Now at this particular edge, so after some time this is the flip flop 1 Q, that means output from the flip flop Q. So that is very much okay. So as this one is the, that means this one is what? This one is the NAND gate. So the delay will be very much shorter. So the delay is only this much. You see, only this much delay that occurs based on the corresponding NAND gate. Now for the second input, that means second flip flop, what is happening? The clock edge basically occurring at this particular edge, right, because of the buffers. So at that time this data is basically changing because of the very short delay. So as this particular edge, the data is not stable, So, at that time you will not get the corresponding value, you may not get. Okay. So, at that time you can get or you may get some of the unstable state. Okay. But actually that will be at this particular age, this is changing the value. So, at that time you will not get the that means the value here properly. It may be 1 or it may be 0, it will be in a ambiguous state. So, then again you take another example, that means from this inverter we are having that means this kind of circuit. So, at this particular path we have a shorter, this is shorter path. Why shorter path? Because it has passed only 2 gate delay, but in this path we have 3 gate delays. So, this is the longer path. So, a synthesis, optimization or analysis tool can perform timing checks on the following types of paths: the clock paths or the clock gating paths or the asynchronous paths or the data to data check path. Okay. So, what is clock path? Clock path is a path from a clock input port or cell pin through one or more buffers or inverters to the clock pins of a sequential element. So, clock paths for data setup and hold checking, clock gating path for clock gating setup and hold checking, and asynchronous path is the path from an input port to an asynchronous set or clear pin of a sequential element. So, asynchronous path has been checked for recovering and removing the corresponding violations. Okay. So, these are the checks that has been performed during the synthesis and optimization purpose. So, again there is another of the example that okay, so that means whatever we have mentioned here, that okay, this is what is clock path, what is clock gating path, what is asynchronous path, what is data to data check path. If I want to, that means show you on in a circuit. So, this circuit shows you all these paths. So, in the first flip flop, the preset value has been NORed with some other logic, whether that may be enable logic or some other logic with the reset value, and that has been applied to the preset value. So, this is the asynchronous path. Okay. Then the corresponding here clock source has been connected directly, and here in the second flip flop it has passes through a inverter. So, this is the, that means the clock path, this is also. So, this is the clock path where this clock port, this is the clock port which is connected with the corresponding pins of the sequential element which are present in the current design. Then I need to, if I need to, that means do this clock gating. Clock gating means in some time the that means the corresponding clock will be off. If in some condition I need to stop the clock. So, that is at the time what will happen, this is one signal which has been ended with this corresponding clock and it has been applied to some other sequential element. So, this signal is basically clock gated, that means the clock is ended with some other signal. So, that is why this is known as clock gating. Then what is data to data check? So, that means this is the data which is available at the very first that means sequential element, then it has been passes through this flip flop, then logic, then again it is arrived at the second flip flop. So, this is the path for data to or data path or data for data to data checking, that means from one path to the one register to the another registers. Then again suppose you see one of the example, another example, that is here I have two flip flops and I have the logic has been placed something like this. Okay. So, here you see this logic, there is two paths, one path is this, the A input that has been passes through this register element, and then the logic element in between, and it has appeared at Z, and there are direct paths which has been passed through this logic. This is purely combinatorial path which is also arrived at this particular path Z. So, here you actually, if you see that each path start at the data launch point, passes through some combinational logic and ends at a data capture point. The path 1 starts at an input port, ends at the data input of a sequential element. Path 2 starts at the clock pin of the sequential element and ends at the data input of the sequential element. Path 3 starts at the clock pin of a sequential element and ends at the output port. Path 4 starts at input port and ends on the output port, right. So, now what is the definition of false path? False path is that means if there is a path, but which is not basically affecting the critical path, which is not coming into the picture of that. So, that means here, as there are two paths which are basically connected from A to Z. So, this path 1 and another path is this one. So, which path is not the critical path? So, that path will be known as this false path. And then this multi-cycle path is that if one path is taking more than once, that means if one from input to the output, if that is taking more than one clock cycle from launch to capture edge, that means from launch edge to the capture edge. So, that is known as this multi-cycle path. So, here you can put this input the same circuit. Here again, if it has been passed through another that means registers. So, this is the input delay I am that means putting, okay. This is the example of that input delay, and this is the, that means at the output side, this is the example of how, that means this is the example of the output delay, right. And how we can, that means calculate this delay, what are the, that means parameters which affects the delay. So, that we will cover in the next lecture. Thank you.